We're going to continue describing solids in R3 with cylindrical and spherical coordinates. One thing that we notice is that we are using angles as part of our coordinates. And the other thing that we know is that angles have lots of different representations. The angle 0 is the same place as the angle 2 pi, is the same place as the angle 4 pi, is the same place as the angle 6 pi, and so on. And then multiply that whole thing by -1, and you get the idea. There's a lot of representations for theta. So what we're going to do is we're going to restrict what thetas we are going to look at for our coordinates. And then modify accordingly. We're going to let theta go from 0 out to 2 pi. If we let theta go from 0 to 2 pi, that covers all the way around our cylinder. So that takes care of every point that we could use. So we're just going to say theta is from 0 to 2 pi. So we're going to restrict theta to be from 0 to 2 pi. Notice that we wrote theta greater than or equal to 0, but strictly less than 2 pi. That's because I don't want two descriptions for one location. So 0 is in, 2 pi is out. If we end up at 2 pi, we're going to say 0 instead. 0 to 2 pi. So starting at 0, ending before 2 pi. Greater than or equal to 0, strictly less than 2 pi. Also note that if I'm at 180 degrees at a radius of r, I could also think of myself at being 0 degrees at a radius of -r. So instead of turning 180 degrees and going forward r degrees, I could think of staying facing 0 degrees and go backwards r. So I don't want two coordinates for the same location. So we're going to restrict r to be greater than or equal to 0. We could interpret things with r being negative, and then we just take the opposite of theta, subtract theta from 2 pi, whatever we would have to do. 90 degrees and 270 degrees. 90 degrees with a positive r is 270 with a negative r. Let's just restrict r to be positive. Let's restrict theta between 0 and 2 pi, and then we'll have nice. We'll have one description for each location. Unless we need r to be negative, and unless we need theta to be outside of this range. Unless we need something else for some particular purpose. Yeah. In general, this is going to be our default. We'll do the same thing. Z can be anything it wants, positive and negative. It's just a distance. No problem. In the case of spherical coordinates, we're going to do a similar thing. Rho is going to be our distance. So let's restrict rho to being positive, or at least non-negative. Let's keep theta in between 0 and 2 pi. Now theta is getting us all the way around, so we have to be careful with our angle phi. Phi equals 0 is the positive z-axis. We only need to go down to the negative z-axis. We only need to go through pi radians. If we go through 2 pi radians from the z-axis, we're going back up to the positive z-axis. We're going to get some points counted twice. So phi, we're going to restrict between 0 and pi. Right. Okay. Of course, we could use those different descriptions. So like if you happen to have an apartment that's in the basement, you could say you were on the negative first floor, but we don't normally say that. We say like zero, we don't say zero is the ground, then we have the first floor, second floor, third floor, and then the negative one floor, and then we kind of do because on the elevator it says B1, that's just negative one. Yeah, but it's negative one. That's just not how we say it. I guess it's different if you talk about story. Like in England, the second floor is the first story. This is because they just messed everything up. I don't know what is wrong. This is why you take no criticism from any British person about how Americans use the English language, because we are unequivocally better at it. It's a better version of English. It is just a better version of it. Because it's been through, they have like English 1.0. Never get 1.0 software. It's like, well, here's version 1.0. It's like, I don't want that. I want to work out the bugs. I want you to work out the bugs. I don't want a beta test, right? Unless you care Cybertruck, then you go buy one because you want to beta test that thing. So this is, of course, unless we need something else. All right. So one of the useful things that we have now that we're saying what's x between, what's y between, what's z between, what's r between, what's theta between, what's z between, what's rho between, what's theta between, what's p between, is that we have more powerful graphing machines now. So if we switch over to, let's say, Desmos, if we take a look at what we have on here on Desmos, I have described this region. Let's just get this red region down here. I've described this red region, this quarter circle in the fourth quadrant, circle of radius 4. And I'm describing it how we would describe it to a double integral. I'm saying y goes between the negative square root of 60 minus x squared and 0. That gives us the bottom and then the top. And then in curly brackets, I say only do this for x between 0 and 4. So if I change the values of x, here I'm changing my integral dx, negative 4 to 4. So then if I go from x from negative 4 to 4, then I get this whole bottom half of the circle. There's that region. This second line that I have here where x is equal to 0, x equals 0 is just a vertical line. So if you just type x equals 0, that will give you a graph on the y-axis. Make it different colors. So x equals 0 is going to give you a vertical line. That's the y-axis. That's the equation for the y-axis in rectangular coordinates. And what I've done is I've just restricted the x equals 0 for y between negative 4 and 0. And so that fills in this line that isn't normally visible. I just wanted to highlight that. If you would recall, last week on Wednesday, we had some polar coordinates problems, and I truncated this quarter circle. I cut off the values for x between 0 and 1. Was it 1 or was it 2? I think it was 2 because it was at the square root of 12. So graphing wise, I just need x go from 2 to 4. So I just get that little slice there. Then we had to figure out where this point was down here. Negative 3.464 is apparently where it is. It won't let me highlight it. We can figure out where that is because we know what x is and we know what that circle is described as. If x is equal to 2, then that is going to be the negative square root of 16 minus 2 squared. So that'll be negative square root of 12. So if I want to move my this other border, that's where x is equal to negative square root of 12. Oops, x is positive 2. Sorry, positive 2. I got this totally backwards. So if I move that line over to x equals 2, we're not going from 0, negative 4 to 0 on the y. The bottom of that line is at the negative square root of 12. This is where I wanted the negative square root of 12. Now it lines up. It still won't, oh, it'll even let me highlight it because it's the intersection of 2 points, two curves. Any questions? Negative 3.464 is the approximation of the square root of 12 with 4 significant figures. But here we have the description that we came up with last Wednesday. What's x between? X is between, y is between negative root 12 and 0, and x is between 2 and 4. Is everybody okay? We can turn this around the other way. We could say y goes from negative root 12 to 0, and then x goes on the left from 2 up to the square root. But if you type in a function, you can type in a double inequality for what's y between, and then in brackets, in curly brackets, you can put the range of inputs for those outputs. Only do this inequality for these values. Any questions? Comments? Slide remark? This is with just x and y. Now notice in the second part, we are a little bit more limited as far as polar coordinates go for in Desmos. So here I've written r is less than or equal to 4 for theta between 3 pi over 2 and 2 pi. From 3 pi over 2 to 2 pi, that gives us the fourth quadrant. R from 0 to 4 is giving that whole quarter circle. What we need to do is figure out how to chunk off from this vertical line. What happens if we want to try to draw this vertical line? So what we need is an equation for that vertical line, x equals 2. I need that x equals 2. Now, in the y coordinates, easy to identify. It goes from negative root 12 up to 0. It's easy to see what y is between. But for theta, it's more complicated. Theta starts off at whatever this angle is and goes up to 2 pi. So I might want to do something like r equals, but if I just do r equals 4, and then I restrict theta from, I'm just going to put this in and adjust it. So that's just r equals 4. If I start bringing up theta after 3 pi over 2, what is 3 pi over 2? 4.7. If I start bringing this up, that's about where it starts. So if I go up to 5, let me turn. There we go. If I bring r up to 5, that's where theta starts, and then it's r up to 6. That's going to be too far. 5.5. This is not very efficient. 5.3, 0.2, too far. 0.25. Pretty good. But if I change this to r less than or equal to 4, what's going to happen? I'm going to get this part of the circle that I want. But if I trade r less than 4 for a less than or equal to 4, what's going to happen to my, are we going to get the right region? Let's find out. That's not going to give me what I want, because that's going to give me all the way back to the origin. It's going to give me the correct arc that we're looking for approximately, because at 5.25, that was a lucky guess. But we're getting all this stuff when x is between 0 and 2 that we don't want. We have to start r at the line. We need a description of that line. Moreover, the description of that line has to be an r equals, because Desmos can't graph theta equals. It's kind of a bummer, but I can't graph, let's say, I can't be like all theta equals pi. It's like all no, you can't graph theta as a function of anything yet. So the problem is that we need r, it's not a constant 4. R has to start off at something before 0. And it has to be variable. Note that up here, when theta is equal to 2 pi, I need r to equal 2. And then when theta is equal to whatever this is, 5.25, I need r to equal 4. So I need my radius to be variable. Any questions? What we need is a description of that vertical line. We need a description of that vertical line. So somehow we need to describe this vertical line, x equals 2, but in polar coordinates. So fortunately for our heroes, I happen to write down the relationship between rectangular and cylindrical coordinates, which includes the relationship between rectangular and polar coordinates. Up here, I have x is equal to r cosine of theta, and I want x to equal 2. So I can say x, if x equals 2 and x equals r cosine theta, I can say r cosine theta is equal to 2. I can solve this for r and write r is 2 divided by cosine theta. Or we could write this as 2 secant theta. So let's go back to the graph and see what r equals 2 secant theta looks like. So r equal, oops, turn this one off. R equals 2 secant theta is in fact giving us that vertical line. And furthermore, we've restricted it from theta is equal to 5.25 to 2 pi. So down here, it's not going to let me trace it. Oh. Down there is where theta is equal to 5.25. And then up at the top where the radius is 2, our radius is, when theta is equal to 2 pi, 2 secant 2 pi will give us 4. Now we might want to get a better estimate of that 5.25, because that was just kind of like guessing.
Very good guess.
That was a pretty good guess. The pixels are big enough that we can't see the difference. I set the graph to have a thick enough line that we really can't see the difference. So we're pretty good with that. One of the problems that we do run into is that R should start off at this line and go out to 4. Unfortunately for our heroes, as far as Desmos is concerned, if I start at 2 secant theta, I can't double inequality. We only plot double inequalities of X and Y, which tells me that they're not even trying. They're not even trying to do double inequalities of radius of in polar coordinates. But they got polar coordinates, so that's the thing. Any questions? Yeah, I do, but not today. So what we did was we took our relationship between x, r, and theta. Our relationship between x, r, and theta. We were able to solve for r and write an equation in polar coordinates of that vertical line. Now, this is relevant to the activity that we were working on yesterday, because yesterday I asked you to describe a cylinder in spherical coordinates. And it's very inconvenient to describe a cylinder in spherical coordinates, especially because we have cylindrical coordinates. But describing the cylinder in spherical coordinates isn't the point. Getting there is the point. And we can do the same thing. When we're describing a cylinder, so yesterday this was what? One of the things that we might want to describe, if we're describing that cylinder with a radius of 3 and a height of 5 in spherical coordinates, the top of that cylinder, the most reasonable place to put it would be z equals 5. We can literally put it anywhere we want. I just decided to put my cylinder from z equals 0 to z equals 5. That's how I represented the height of 5. If you're like, oh, no, I like things in the middle, so I went from z equals negative 2.5 to z equals positive 2.5. I mean, you do you. You put your cylinder wherever you want. I will not stop you. But this will work wherever. What we want is that z equals 5 in spherical coordinates. We want z equals 5 to be described in spherical coordinates, and we can do the same thing what we did with the polar coordinates and the vertical line. Down here, I have a relationship between z and I have the coordinates of z. I have the relationship between cylindrical and spherical coordinates. So if I write z is equal to rho times the cosine of phi, then rho cosine of phi is equal to, we want that to equal 5. And so we could solve for rho as 5 over cosine phi, or we could say rho is 5 secant of phi. So rho equals 5 secant phi will give us a horizontal plane at z equals 5. If we think about what secant looks like, or better yet, if we think about what cosine looks like, when phi is equal to 0, cosine of 0 is 1, and so rho is 5 over 1. Then as phi increases to pi over 2, cosine drops down from 1 to 0. 1 to 0. Think about the unit circle. The x-coordinate around the unit circle goes from 1 down to 0. So cosine of pi over 2 is 0. So that means rho is going to be infinite. So what happens is that we maintain this horizontal z equals 5 as theta goes away. When theta is equal to pi over 2, we don't get anything. It's undefined. But as theta approaches pi over 2, our rho is approaching infinity. Fortunately, we're going to be cutting that off before we get to pi over 2. Because we only need to describe that circle on the top of radius 3. Any questions? Comment? Snide remarks? How's everybody okay? I can't tell if everybody looks stunned. I took my glasses off, so I can't see faces. I can see kind of like blur. What? So in an integral, this is going to require that we be mindful of the order. We might not be able to get all 3 orders of d rho, d phi, and d theta. What we're going to set is rho will start off at 0. That'll be down at the bottom. And rho will go up to this plane, 5 secant phi. So that means this rho is going to have to come before phi. And then we'll be able to calculate what phi we want. So I'll set my d rho integral. Rho will start off at 0. And then rho will go up to 5 secant phi. That means my phi integral is going to have to come later. When phi equals 0, that's going to be the point on the z-axis. I know we don't have a z-axis spherical coordinate. But that phi equals 0 is going to be at the phi on the z-axis and then move away. So phi will start off at 0 and then go up to, well, this is 5, r is 3. we can calculate where phi is going to be. So if we grab a 5 here and a 3 here, that's where we want rho to stop. That's where we want phi to stop. And since 3 is opposites and 5 is adjacent, we can say that the phi is a tangent inverse of 3/5. Since we want the cylinder to go all the way around, I want that full cylinder. What's the range? What's the interval for theta? To go 0 to 2 pi. And that 0 to 2 pi could either go before all this happens or to go last. So I could either put my theta equals 0 to 2 pi after this, or we could put it before, since the theta doesn't have anything to do, it isn't involved in rho. But phi is going to have to come after rho. I can even put theta in between. But I'm definitely going to have phi come after rho, because the way we get that flat plane is to describe rho as a function of phi. Any questions? Okay. I just dropped a bunch of trig on you. It's all kind of sketchy about how much trig we have walking into any context. You get through calc 1, it's like, oh, trig didn't really come up that much. Derivative of cosine is sine, negative sine and stuff like that. But all right. So that's how we get flat stuff that's not through the origin in cylindrical and spherical and polar coordinates. We just rely on those relationships. The things like vertical lines and horizontal lines are very easy to describe in rectangular coordinates. Things like horizontal planes, vertical planes, I don't know, perpendicular, horizontal / vertical. Those flat planes where one of the rectangular coordinates is equal to a constant, those are easy to describe in rectangular coordinates. It gets messy in round coordinates. Just like round things are clean in round coordinates, round things are messy in square coordinates. No surprises there. All right, that's going to do it for today. I will see y'all on Thursday. Reminder, there is no meeting tomorrow. Say that again? No, we also have to have like 2 factors that turn T into a length, and say we can use rho for T, but we need R for theta. So we have a relationship between R and rho. Oh, to answer your question, yes, we are the same.
No, I got have you ever scanned that? No. But some dudes like there's like the